So the first thing is Wednesday is exam 2. And the topics for that are everything up through circular motion. And circular motion is still particle kinematics. You know, particle kinematics. Even though it's separated, even though I separated it into 2 sets of problems, that still would be described as 2D particle kinematics because you're still just talking about relationships between position, velocity, acceleration, and time. Yep. Oh, yeah, that's right. So for half of the class, if you can, I'd like you to bring in your notebooks on Wednesday. If you can't, or you want a couple extra days to get some stuff done, that's actually fine with me too. But the more people that bring it in on Wednesday, and I can get started on the first half of the class, the better it is. And then I think the other half of the class, it's separated by lab section. The other half of the class is like next week sometime, just so I can, instead of getting a giant pile, I can get 2 smaller piles. And so it's supposed to be broken up into what lab you're registered for, not necessarily the lab you come to, So yes, please, if you can, bring your notebooks on Wednesday, your binders. Yep.
I'm looking through the syllabus on the binder section, and it wasn't clear to me on whether or not we had to include the solution put online in there.
You don't have to. I think for your own, I wouldn't mark it off if you don't have those, but I think they are useful to have in there for future reference. Basically, like everything that I tell you to put in there is I'm just trying to make it as useful for future reference as possible. It's nice to be able to look at that stuff. But if you do all the homework, in the right amount of detail and everything, those work just as well. So, any other questions about? Yes.
Can I see you work one homework problem?
Sure. Yeah.
It's number 14 on 2D.
Okay.
You need the.
Yeah, I do. Any other questions before I start a homework question about the exam or? Oh, actually, and before, yeah, hand that up, please. But we also have our lab exam on Friday. Thanks. So lab exam 1 is on Friday, and that's going to be questions that were asked on the labs. It's not going to include the circular motion stuff that we did last week. That was just to help get ready for this test. So it won't include last Friday's circular motion problems. Yeah. So it'll be questions like showing you a position versus time graph, and you have to figure out where the thing is moving in the negative direction, where it's speeding up, that kind of stuff. It'll also be stuff like I'll show you the 2-dimensional path that an object travels and tell you whether it's speeding up or slowing down. And you have to figure out what you know about the direction of acceleration parts and that kind of stuff. Okay. So yeah, any questions about the lab exam? I think now all of the labs that we've done, there are PDFs of those up on D2L. if you go into lab, I think it might say lab manuals or labs. So you can pull up the old labs. And I think if you're comfortable with those kind of questions, everything will look familiar on the lab exam. Okay. What number did you say?
Number 14.
14. Okay. So 2D particle kinematics. Number 14. An object is dropped inside a moving vehicle. And a camera inside the vehicle. Measures the object's acceleration as -5, -11.5 meters per second squared. What's the acceleration of the vehicle? So this is a relative motion problem. Relative motion problems you can always think of as having, there's always some kind of ground, so let's say G is equal to ground. And when I say ground, I don't necessarily mean the dirt, the floor or whatever. I mean, it's just something that's fixed, something that's connected to the earth. And then there's some kind of vehicle or intermediate thing, an elevator or a car or a, animal's stomach or whatever. They're, anything, but it's something that's moving compared to the ground, but then there's something moving inside of that thing. Okay. So that's the vehicle. And then there's some object. And I'm doing this with acceleration, but it's the same approach if you're talking about position or velocity. I just always set up this equation as the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the vehicle plus the acceleration of the vehicle relative to the ground. And one kind of problem that we've seen a bunch of times is where you have something in free fall, and so you know what the acceleration of that thing is relative to the ground, and then you use that to figure out the relationship between the object and the vehicle in some way or another. So in this case, the object's acceleration relative to the ground is 0, -9.81. What we're given is the acceleration of the object as measured by the vehicle. So this one, in this case, is -5, -11.5. And we're trying to find the acceleration of the vehicle relative to the ground. And now it's just algebra. We can subtract this vector from both sides, and we get that 0, -9.81, minus -5, -11.5, is equal to the acceleration of the vehicle relative to the ground. And so you get positive 5, and then what's 11.5 minus 9.81? 1.69. So I'm assuming that we're using a coordinate system with the y-axis up, and the x-axis then has to be to the right. This says that in order for something in free fall to look like it's doing this, the camera has to be doing this, accelerating 5 meters per second squared to the right and 1.69 up. If you have a way to take measurements on your phone or like look in slow motion at locations or whatever, next time you're on an airplane, you should do a little experiment as it's taking off or whatever. You can measure the acceleration of the airplane that way. You'll probably get chosen for random screening afterwards, but I think it's worth it in the name of science. Any other homework questions anybody wants to see? Okay. So now we're going back onto the new stuff that is not relevant for this exam. So the new topic is particle kinetics. And this stuff is not going to be on the test on Wednesday. And what we started talking about was the most important equation in this class, Newton's second law. And Newton's second law says that if you add up all the forces acting on some chosen object, that's F net, and forces are vectors, so you have to express them in components and then add them. That's equal to the mass of that chosen object times the acceleration of that object's center of mass. I defined mass, and really up until now in this class, we've been mostly talking about what these accelerations mean. So we know how to calculate the acceleration of an object. We know what the mass means. Now we have to focus on what these forces are. Usually, we're not going to want to know something about the net force. You know, we won't want F net itself. We'll want to know something about the individual forces that make up F net. So in a case like that, you always need to draw a free body diagram. And I'm going to abbreviate free body diagram, FBD. So we're going to basically use this anytime we use Newton's second law. The only exception is if it asks you specifically for F net, then there's no reason to do this because it's really only helpful if you're trying to break up into individual forces. But okay, let's talk about what are the requirements for a free body diagram. The free in free body diagram, or the free body, means the only thing you draw is the chosen body. Any other objects are only represented by the forces they apply to the chosen body. So any other objects show up only as the forces they apply to the chosen body. Okay, so here are the steps for drawing a free body diagram. So let's say, as an example, as I do this, I'm going to do a free body diagram of this car. There's a person standing on the car. The car is super cool looking. It's got some flames, some lightning bolts. There's an American flag because flags are rad. Okay, so let's say that we want the free body diagram of the car. So the first step is draw a closed outline of the chosen object and this closed outline should not include any internal details or any outside objects. Okay, so in this example, that means that I'm going to draw an outline. It doesn't have to be very artistic, but okay, so there's an outline of the car. It doesn't have any, it doesn't show the lightning bolt or the windows or the hubcaps, and it doesn't show any external objects, okay? So here are some examples of things that don't meet these requirements. Okay, that's not an outline. because it doesn't say anything about whether we're including the top of this line in our chosen body, or, you know, the top of the hood or the trunk, and the wheels are closed on their own, the top is closed on its own. We want an outline that makes a very clear distinction between what's included and what's excluded. Okay. How many people here took physics before this? Any physics before? Not a ton of people, a few. I think it's probably pretty likely that in your physics classes before, when you did free body diagrams, you did them as a point, and then you drew the forces going in the different directions. There's a reason that we're going to start doing it differently now, and that's that almost everybody in here is going into engineering. And drawing your free body as a point is useful for particle calculations, okay, where you assume everything is happening at a single location. But it's not useful if you're treating things as rigid bodies, where you can make distinctions between different orientations of the body, okay? Because, so if you're treating something as a particle, then there's a force acting on this wheel and a force acting on this wheel and a weight in the middle or whatever. But if it's a particle, you treat it like it's all acting on the same thing. So drawing this as a point and just different arrows in different directions is fine. But pretty soon, we're going to want more information than that. And like, for example, if you have a 5,000 Newton force on this wheel and 40,000 Newton force on this wheel, it adds up to a total force of 45,000 newtons. But that's not the same as applying a 45,000 Newton force through the center of mass. One of those would keep it horizontal, and one of those would rotate it, you know. And as a car owner, it's really important that you don't, you know what I mean? There's a big difference between your car being on its roof or not. Okay, so yes, so if you're used to drawing your free body diagrams as just a point with arrows coming out of it, you're gonna have to change now, and you'll be happy you did when we get onto rigid bodies. Okay. So this won't work. This won't work. Where you're like, yeah, I did the outline of the car, but then I had to get that rad flag in there. That won't work. Because all we're trying to do is be perfectly clear about what's in the in crowd and what's out. You know what I mean? This, that boundary is everything. And I'll explain why as we go. But the boundary between the in and the out is everything that we care about. Okay, so once you have that outline, the second step is represent all forces acting on the chosen object. By an arrow pointing in the direction of the force. And a value or variable that's going to represent the magnitude of the vector. Okay, so the magnitude of a vector, is that a number or a vector? The magnitude. It's just a number. So this is a scalar. You know, a scalar says that is just a numeric value or a single variable, not a vector value or a vector variable. Okay, so for the example that we're doing here, we haven't talked yet about how to know what directions these forces are applying, but I'm gonna put the directions here. But that's a lot of what we're going to talk about in the next day or two. So there's a weight force, and then each of these two wheels has an upward force applied to it by the ground. I'll call this N rear and N front. And then what else is going on? There's a guy standing on the hood. So there's a contact force of the feet of the person pushing down. I'll call that R. Okay. And now every object that's applying a force to this car is represented by a force vector. Well, this mg usually is known. We usually know the mass of the object, so forget about that one. But we have three of these things left over, and that means that if we go into Newton's second law right now, we would have three unknown values that we'd be trying to calculate. Okay. And if you're doing it, you know, since we're starting out with particles, we're starting out with particle kinetics. Two of those forces are applied to this object by a single thing, the ground. Okay, and so for now, breaking it up into the rear and the front isn't really necessary. So you can just do it as the weight force, a combined force from the ground, and then the force from the person. But like I said, when we start talking about rigid bodies, it's going to be important not to do that, but we have plenty of time for that. Okay, so this is a complete free body diagram. Now, before we go into talking about the directions of individual forces, I think one thing that's always going to be important to keep in mind is how do you know once you've represented all the forces? So how do you know if you've represented all the forces? Yep.
If you know the object isn't moving, all the forces should add to 0.
That's true. That's not what I was getting at right now. But that is going to be a useful thing. So, like, look at this complicated, you know, sort of a complicated picture. There's just a lot of stuff going on. There could be a million people milling around or whatever. How do you look at a picture like that and know whether you've represented all the forces? Well, there are only two types of forces. And if you've dealt with all of those types of forces, you know you're good. So the two types of forces are first, what I'm going to call field forces. And by far the most important of those for us is gravity, but that could also involve magnetic fields, electric fields. There's probably other ones. So basically, we're only going to deal with gravity, and that's a downward force with a magnitude of mg, where m is the mass of the chosen object, and g is the acceleration of gravity in free fall, 9.81 meters per second squared. Okay. If you have an electric field or a magnetic field or whatever, things can get a lot more complicated, but we're not going to really have to deal with that. So for us, you just have to make sure that you draw that weight force in there. And then after you've dealt with the weight and any other field forces that are happening, there's only one other type of force that you have to deal with, and that's contact forces. And that's forces that are applied to the chosen object by the surroundings at the boundary. And that's why we want to be so careful about defining what is the boundary between what's in and what's out. So let's look at this object again. In order to make sure that you represent all the forces that are applied to this object, we first show the weight force, this downward force of mg. And now the only thing we have left to do is mentally go around the boundary and think about, at that point on the boundary, is there any contact between the surroundings and the body? Okay. Once we've dealt with all of those places where there's contact, we're done with the free body diagram, and we know that we have every force represented. Okay, so there's a weight force, and now I'll just start arbitrarily at the front wheel. There's contact at the front wheel, so you got to put something there. Keep going around, nothing, nothing, nothing. Up here, there's the guy standing on the hood, so we have to put some kind of force there. Nothing until you get to the back wheel. There's contact between the surroundings and the boundary there, so you need a force there. Go around, and then you're done. Okay. So no matter how complicated the thing is, your free body diagram, to do your free body diagram, you're going to represent the weight force, and then you're just going to go around the boundary looking for contact. And once you're done with all the contacts at the boundary, you're done with the free body diagram. Okay? Okay, so for the gravitational force, I said the direction that it acts, it's always down. And By the way, notice that this doesn't say anything about what the object's doing, whether the object's flying through the air or sitting on a table or whatever. The gravitational force is always the same. Okay, so if you're ever asking yourself like, wait, is there gravity here, or does this change it, or whatever? In a way, you're already thinking about it too hard. The answer is gravity always applies a force magnitude mg down. And like, oh, but what if I'm floating in a tub of goo or whatever? Well, gravity still applies that weight force down, magnitude mg. It's just the goo also applies a force upward that keeps you from sinking. Okay. I just wanted to say tub of goo. All right, so we know the direction of the weight force. Now we have to think about the directions of various types of contact forces. And there are going to be 4 of these types. The first one is a pushing contact. And a pushing contact is one where, so if this pushing contact force didn't happen, the 2 objects would blend into each other. Okay, so it resists like merging. The second type is a pulling contact. And an object is pulling on another object if that force is preventing the 2 from separating. So this resists separating. The third one is a friction force. And the fourth one is a spring force, a force applied by a spring. The first 3 seem it's pretty intuitive that those come up often enough that we'd want to deal with those. I think probably to a lot of people that fourth one seems pretty random, like your parents' house has a junk drawer in it that has like springs in it, but it also has like a broken pair of sunglasses and like some glue or whatever. Like, why aren't we doing sunglass forces? You know what I mean? The answer for that is that actually the kind of forces that springs apply are called elastic forces. So really that's the start of talking about elasticity. And elasticity is a really useful idea in engineering. When a machine applies a compressive force to a piece of steel or whatever, that compressive force makes the steel shorten a little bit and bulge out on the sides a little bit. It's very little because steel is really stiff. But that process is elasticity. It says that you apply a force, you get a change, you get a deformation of the material. When you remove the force, the thing goes back to its original shape. And a lot of important engineering stuff depends on that idea. So really, don't think of this as us doing calculations involving springs like that you get at the hardware store. Think of it more as like an introduction to this idea of elasticity that's going to be important. Yes? Yeah, exactly. So springs do that, and that's exactly what a trampoline. So, yeah, if you think of the word elastic, I think like looking back, what I thought the word elastic meant before physics was sort of like, well, it stretches, or you think about the elastic waistband of your pants or whatever. And like, yeah, trampoline, you apply a force to the surface and it stretches. But that's not what elastic means exactly. The more important thing that elastic means is that when you take that force away, the trampoline goes back to its original shape. And like if your sweatpants band was made out of Play-Doh, you know, it would still stretch, but it would miss the crucial part of sweatpants bands that when you let go of it, it goes back to the side. You know what I mean? So elasticity is saying you apply a force, you get a deformation, you remove the force, the deformation goes away. Okay, so do we have time for any of this? Well, yeah, let's talk about pushing contact, and we'll finish this next time. So if two objects are pushing on each other, so when an external object pushes on the chosen object, it applies a force that's perpendicular to the surface of contact and toward the chosen object. Okay, so let's think about two objects that are in pushing contact. So let's say that there's a block. Let's actually make it, give it wheels so it's easy to imagine it without any friction acting on it. And let's say it's in contact with a ball. Okay, and let's call, like a sphere. Let's call this body 1 and this body 2. And let's say that there's some force of 10 newtons applied to this one. I'm going to draw free body diagrams of each of these. So first I'm going to draw a free body diagram of that little cart thing. So assume that that's the chosen object. So there's the outline. And the force is acting. There's a weight force that's equal to the mass of that, I'll call it M1, times 9.81 meters per second squared down, so M1G. And we know it's acting downward. And then going around the boundary now for the contact forces, the ground is pushing on the wheels, okay? How do we know that's a pushing force? Because if the ground wasn't there, the cart would merge into its space, okay? So that's a pushing contact that's preventing those two things from merging. We actually have one of those at each wheel, but for now as particles, we can just treat it like it's a single one. I'll call this N1. I'm going to use that variable n a lot for normal force, but really that's not conceptually important. You just have to know that that's a variable representing the magnitude of that pushing force. And then on the right side, that ball is pushing on this object. It's pushing because that contact is preventing them from merging. So there's a force this way, perpendicular to the surface of contact toward the chosen object. And I'll call that R. Keep going around the boundary, and the last thing is the given force of, and we don't have to know what's providing that. The work's already been done for us, so 10 newtons of force that way. Any questions about that? So we had two pushing contact forces there, the one from the ground and the one from the ball. Yeah.
Why are you labeling that R on the right? What's the significance of R?
Oh, R is for reaction. So again, conceptually, it's not important. You're just giving it a variable name, but N's and R's are normally used for pushing contact forces, but it's just a variable. This is the last thing, so, and then we're done. Free body diagram of body 2. So this is the ball. There's a weight force that's equal to the mass of the ball times g. And now go around the boundary looking for contact. There's a pushing force from the ground, and I'll call that N2. Keep going around. Over on the left side, there's a pushing force coming from the cart. And now, notice that pushing, the force the cart applies to the ball and the force the ball applies to the cart represent this pair of contact forces between two objects. And when you have that, when you're just switching from the contact force on from 1 on 2 to the contact force from 2 on 1, they have the same magnitude. We'll talk about that more later on. But whatever the value of the first one is, that's the value of the second one. That's going to be a super useful thing. It's actually called Newton's third law, and we'll get to that. Okay, last thing. Just notice this one last thing. What about that 10 Newton force? That's right. Like, this can be a little confusing because whatever motion happens from that ball is going to depend in some way on that 10 Newton force. But when you're figuring out the forces that apply to this, all you're doing is putting in the forces that are acting around the boundary. This 10 Newton force isn't acting on the boundary of this, so it doesn't show up. It does show up indirectly. If you increase that force, it'll make that R force bigger, but it doesn't directly influence that. It doesn't directly apply to the boundary, so you don't put it in there. Okay? So if you sort of keep it simple and keep thinking about the rules, it's easy to avoid mistakes. Okay, that's all. Okay, yeah. Yeah, it's an easy one to make, yeah.